Hello everyone. In this tutorial, we're going to implement score-based generative model through SDEs or stochastic differential equation. So basically, the concept is same as of diffusion models, where we first perturb or noise our input data, and then we perform reverse sampling to remove the noise and generate our original data. So first of all, as in diffusion model, there is a forward process and reverse process. In this tutorial or in this project or in SDEs, we also have this forward and reverse process. In the forward process, you can see that dx is equal to sigma t dw, where x is the data that is progressively noised over time, and dw is a standard linear process, which models the random fluctuations in the system. The term sigma t is a time-varying diffusion coefficient controlling the scale of noise added at each time step. As the time t progresses, the noise added to the data grows exponentially because of the factor sigma t, thus making the data increasingly noisy. And the second one is marginal standard deviation. This equation basically calculates the marginal standard deviation at time step t in the forward diffusion process. It shows how much how much noise has been added, growing the sigma raised to power 2t but controlled by 2 log sigma for smooth increase. It helps in tracking how the data's variance change over time with large sigma values causing noise to grow faster. The third one is diffusion coefficient. This equation G or GT basically defines the diffusion coefficient, which controls how much noise is added at time t. It grows exponentially with time influenced by sigma. As t increases, more noise is added, making the data noisier. The next part is Gaussian Fourier projection. So basically, it just projects our time steps values into a higher dimensional space for our neural networks for better learning and prediction part. And why this? As I said, it helps neural networks by encoding the time step which are higher dimensional inputs or encodings, so the neural networks can perform better. The next one, this one is a noise prediction model or score prediction model here. It basically consists of convolution and deconvolution operations. So the training process, so we first perturb the input. As we can see, we can perturbing it up to time step t, and then there's a score prediction model that actually predicts the score log probability of noisy data with respect to clean data. So yeah, here you can see that we're calculating the score of the model, score or the log-based probabilities. In score-based diffusion model, the goal is to train a neural network to predict the gradient of the log probability density of noise data at different time steps. So during training, we add Gaussian noise to original data sample to get a noise version, and then model predicts the score, which is basically the gradient of log density at xt. Yeah, and Z is the Gaussian noise that we add to the clean data, and STDO is a standard deviation of the noise at time step t. So this is standard deviation, this is the Gaussian noise. Yeah. Then we train our model. I have already trained it, so we just move to the next part. The next one is the Euler-Maruyama sampler for score-based diffusion model. So in score-based generative modeling, one approach for sampling from the reverse distribution is to use numerical values to approximate the reverse SDE. One of the widely used methods is this one, which basically discretizes the reverse SDE into smaller time steps, enabling the model to iteratively generate samples from noise. This method is particularly useful for score-based models, where score function is learned to reverse the forward diffusion process. So basically, it's trying to say that we have added the noise, and then the score model is predicting the log-based probabilities, and then we are denoising it. So we have the process begin with random initialization of x0 draws from a normal distribution scaled by the marginal standard deviation at time step t0 equal to 1. where sigma t represent the standard deviation at time step t. Then there's a time step. These time steps are discretized from t equal to 1 to epsilon. This epsilon is a small value. And then the time steps are sampled in reverse order from t1 to t0, from t0 1 to down to t1 equal to epsilon. The time steps are defined in this space where we can see the delta t is equal to ti minus 1 minus ti. Then there is a diffusion coefficient at each time step. The diffusion coefficient gt is calculated as sigma t, which is basically used to scale the noise in sampling process. Score model prediction at each time step t, the model predicts the score, or which is the gradient of the log probability of the noise data at time t. So this is our neural network basically that is predicting the score. The score is used to guide the sampling process. Now how we perform the sampling process. So the next step is the processing. It's computed or performing the reverse sampling through the process of Euler-Maruyama discretization. Yeah. So we're going to the next time step. The next time step, or we can say the next denoise sample here. This is the noise sample, and this one is the diffusion coefficient, taking the dot product with the score net, and this one is the change of time. And then we perform the reverse process through this way. You can refer to the paper, this paper, score-based generative modeling through stochastic differential equation, for further clarification. So why it's important? Basically, this process is significant for score-based generative models provide a simple and computationally efficient to sample from complex distributions defined by reverse diffusion processes. This method is based on discretizing the reverse time stochastic differential equation STE, which is used to model the process denoising data samples through iterative steps. The next one is predictor, corrector, or PC sampler for score-based diffusion models. This is also an advanced sampling algorithm for score-based generative model combining both deterministic and stochastic prediction at each time step and improve upon the Euler-Maruyama sampler by integrating predictor step and a corrector step. This two-step process ensures better sample quality and stability. So for PC sample algorithm, the initialization process starts by sampling the initial noisy data x0 from scaled normal distribution, where this one is a marginal distribution, marginal standard deviation, and the second one is time discretization. So the continuous time interval is discretized into n equally spaced time step from t equal 1 to t equal to epsilon, and then we calculate the delta the same way we calculated before. And there is a corrector step at each time step ti. The Lagrange MCMC update refine the sample by adding a scale score gradient and noise. Through this way we have just update our sample at each time step t. Then the predictor step, and after the corrector step, the predictor step approximates the reverse time SD using the Euler-Maruyama method. So this is diffusion coefficient, then we update the mean. This is our diffusion coefficient score model at the time step, and then this is a predictor step. So the significance of predictor, corrector, or PC sampler. The PC sampler improves sampling quality and convergence in score-based diffusion models through corrector, Lagrange MCMC, and predictor reverse SDE. So the corrector refines the sample by iteratively adjusting it towards the high density regions of the learned data distributions using score gradients. It basically balances the score and noise via an adaptive step based on signal to noise ratio. The predictor step basically progress the samples through time using deterministic approach of reverse SDE while incorporating controlled stochasticity. And third one is ODE-based sampler for score-based diffusion models. So the ODE sampler deterministic method for generating samples from score-based generating models by solving the corresponding probability flow ordinary differential equations or ODEs. Unlike stochastic samplers that rely on random noise, this method integrates a differential equation that deterministically evolves the sample from noise to data using black box ODE solver such as Runge-Kutta. Probability flow ODE, the reverse time stochastic differential equation can be converted into a deterministic ODE known as probability flow ODE. So that's how we just perform the reverse sampling. This one is a diffusion coefficient at time step t, this one is a noise predictor model, and xt is the sample at time steps t. So basically we perform the reverse operation by starting from one time and then we go back to the time, like starting from 100 to, and then we go up to time step 0 as we go in diffusion models to remove the noise. The significance of ODE sampler. The ODE sampler offers a clean, noise-free and deterministic alternative to stochastic samplers. Deterministic generation, black box integration, high quality samples. Also support the latent sampling. So this one is the implementation of ODE based sampling, and this is a visualized result on AMD's data. So, you can further play with it. Thanks for watching. I hope you like it. I will also provide the code link so you can go through details in it, and also for further updates you can check out this original paper, score-based generative modeling through stochastic differential equations. Thanks for watching.